Today we are going to deal with some JAM previous organic chemistry problems. These are some advanced problems. Let's start without any delay. See, this is the first question in this series. So if you are given with a problem, you just evaluate the starting material reagent. So here you are given with a conversion. So reactant, reagent, product. So you are asked to identify which type of reaction it is. Okay. So the options are aldol reaction, Cannizzaro reaction, aldol reaction, Claisen-Schmidt reaction, Nevinger condensation, Cannizzaro reaction, Stock condensation, and Cannizzaro reaction. So simply here it is a aldehyde, two aldehyde here. One is aldehyde with alpha hydrogen. So this is aldehyde with alpha hydrogen. So this is a alpha. So you can have three alpha hydrogen here. Three alpha hydrogen. This is aldehyde with there is no alpha hydrogen. So we just check with the first option, aldol reaction and the Cannizzaro reaction. So with this option, a reactant, you should choose a reactant having alpha hydrogen. So let's start with this compound, that is acetaldehyde. Okay. So is having one alpha hydrogen. So in the presence of NaOH, OH minus comes to the picture. It will abstract this proton and it will form enolate or carbanion, right? Okay. So you have a carbanion here. Next, this compound can undergo cross aldol condensation reaction with the given formaldehyde, right? Formaldehyde. So you will end up with a compound like this. A compound like this. This is O minus, it becomes OH under protonation. Here you have two hydrogen. Okay, right. CH2. I simply omit these two hydrogen because in bond line representation it will be there. This is the situation. Now here again you have two more hydrogen. It will undergo one more aldol condensation reaction. One more aldol condensation reaction. So you will end up with the product like this. This is already formed CC linkage. This is the new formed CC linkage. Again one more hydrogen here, right? So it will again undergo aldol reaction. So you will end up with the product first aldol condensation reaction, second aldol condensation reaction, third aldol condensation reaction. In this compound, no alpha hydrogen. Yeah, there is no alpha hydrogen. Now this compound, see, you are given with only NaOH, right? So both Cannizzaro reaction and aldol condensation reaction can happen with the presence of sodium hydroxide. Now this fellow undergo Cannizzaro reaction. Cannizzaro reaction. You know that Cannizzaro reaction give you a carbonyl corresponding acid and alcohol. Okay, so this is your carbonyl compound aldehyde. So this aldehyde undergo disproportionation reaction, and that give you oxidized carboxylic acid product and reduced alcohol. Now your product will be, I am taking reduced alcoholic portion. So this is your one of the aldol condensation product. This is another aldol condensation product. This is third aldol condensation product, and the green one is your Cannizzaro product. Now this is your desired product. So your reaction happen via 3 aldol reaction plus not condensation, no alkene is formed, 1 Cannizzaro reaction. So your answer is A, right? Okay. So next question. The appropriate reagent required for carrying out the following transformation. This type of advanced problem you will have about 1 or 2 questions. So you need to give much more attention. Why? Because each option having a several name reaction. So you have to check out carefully. So for this compound, we want to analyze each and every option, whether these options give you the desired reaction. So first of all, we are going to check whether the first option is giving you the desired product or not. So I am taking the first option. Your starting material is benzyl alcohol, that is PHOH. So I am taking the first option. The PCC. You know that PCC is the oxidizing agent. It will oxidize your alcohol to corresponding carbonyl compound. So give you corresponding aldehyde. Okay, PCC. That is, this PCC oxidize this alcohol to corresponding aldehyde. Now next reagent is triphenyl derivative. That is, we can check. That is PPH3 double bond COOET. This is nothing but leader. This is your Witting reaction. So you know what is the utility of Witting reaction? That convert the carbonyl functional group to the corresponding, so carbonyl compound to alkene. So the basic Witting reaction is nothing but this carbonyl functional group get converted to this function group, provided you are given with PPH3CH2. But if you have any substitution here, that will appear here. Okay, so that is Witting reaction. This is Witting reaction. Okay. So your product will be OET. Okay. Now next reagent is aqueous NaOH. Aqueous NaOH. What will happen? It will hydrolyze. Saponification. So it will hydrolyze and that give you corresponding carboxylic acid. So yeah, I am taking here, that is PH double bond. Now it will convert this carbonyl functional group, that is ester functional group to corresponding carboxylic acid. Okay. Right. So simply that is your product. So right, that is pH double bond. Okay, this is nothing but cinnamic acid. Okay. So option A give you the desired reaction. That is this reaction is multi-selective question, so you have to identify more than one answer if any. Okay, then only you are awarded the respective mark. Okay. Now we want to check next option whether it is give you the desired product. So here our reaction starts with that is benzyl alcohol, and your reagent is that is chromium, this CrO3. Okay, that is nothing but Jones reagent. You are familiar with that reagent, that is CrO3 plus H2SO4 in the presence of acetone. That give you corresponding carboxylic acid, right? That is the utility of a Jones reagent, that convert entire primary alcohol to carboxylic acid, not end up with the aldehyde function group. It give you corresponding carboxylic acid. Now next reagent is acetate. Okay, that is acetic anhydride, AC2O. Two reagent only. Second reagent, that is CH3O acetic anhydride. You know, acetic anhydride react with this acid under acidic condition, not end up with the desired product, right? No, it is not end up with the desired product. It is another name reaction in the presence of NaOH, NaOAC, but it won't give you the desired product. That is acetic acid. It won't give you desired product. It will undergo some enolization here, but that enolate not much reacted with this carboxylic acid. Yeah. Instead of this carboxylic acid, if you have carbonyl compound like aldehyde or ketone, then you will undergo some kind of a Perkin type reaction or non-Perkin reaction, but it won't undergo any reaction here, so it will not give you the desired product. So second option will not give you the desired reaction. Okay. Now we can check the third reagent. So pH, so reagent is nothing but MnO2. MnO2 is now another oxidizing agent. It will oxidize the allylic alcohol, normal alcohol to corresponding carbonyl compound. Here it will give you, it's not a drastic oxidation, it will not exceed up to carboxylic acid. It will give you corresponding carbonyl compound, that is aldehyde. It will give you aldehyde. So this is C, option C, this is D. Now next reagent is CH2CO2 H twice. Okay, that is nothing but another name reaction, Noengel reaction. It is termed as. So let's check what is that reagent. Okay, it is nothing but this reaction. You are familiar with this reagent. I'm writing here. This is an active methylene group. Active methylene group. So you have active methylene here, right? So it readily produce enolate. It readily produce enolate. So in the presence of piperidine. Piperidine is a well-known base. Yeah. So it in the presence of piperidine. So piperidine produce corresponding carbanion here, enolate here, right? Enolate here. So that enolate will react with this your carbonyl compound. This is a name reaction. It is called Noengel. Condensation reaction. So you will end up with the pH O minus, and condensation, that is new CC bond formation takes place here. OH. Okay. Now clearly it will undergo protonation, and here itself some condensation may take place. That is, with we know that piperidine in this system, it is there in this system. Okay, it is there in this system, so it can abstract this proton again. Now, as we seen in the case of aldol condensation, so the same reaction will happen here. So that give you product like this. Okay. Now the all other things are the same. Double bond OH, double bond OH. Now we can see what is the another reagent. Okay, piperidine. Now, so since it is a dicarboxylic acid, so two carboxylic functional group is there, so it may undergo some decarboxylation. So decarboxylation may happen. And CO2, so your product will be, this is your desired cinnamic acid. Okay, so option C also give you the desired reaction. What about D? We can check the option D too. Okay, so first option is PCC. So that already we have seen in the case of PCC, oxidation takes place. So option D is pH. PCC. So that give you oxidation, right? So to the corresponding carbonyl compound, that is aldehyde. That is the first reaction. Second reaction, let's check what is the reagent. It is a alpha halo ester. It is alpha halo ester, right? So we are CH2, CO2, C, CH3 thrice. Okay. So that is nothing but this fellow. BrO CH3 thrice. Okay, OCH3 thrice. Now in the presence of zinc, right? So this is a well-known reaction, that is nothing but Reformatsky reaction. So we know that under the Reformatsky reaction, you will form an enolate. You will form an enolate just like carbanion, and CC bond formation will takes place. CC bond formation will takes place. So what will happen is that, so this fellow get converted to an enolate. Just I am taking carbanion here. So till attack, I am omitting the whole mechanism of Reformatsky reaction. So that give you pH O minus becomes OH, and new bond here like this. O CH3 thrice, and okay, that is the first product. Okay. Now what is the next reagent, or any reagent? You can check, is there any reagent? Yeah, hydrolysis in the presence of heat. Okay, hydrolysis will be there. So hydrolysis, you know what will happen in the presence of hydrolysis? What will happen in the presence of hydrolysis? It becomes OH. It becomes OH. That is pH, OH, C double bond O. It becomes corresponding acid portion. Sorry. pH, OH, and heat also given. Okay. That is, heating condition is favorable for elimination reaction. Okay. Elimination reaction that favor, that is high temperature favor elimination reaction too. Okay. So that give you pH double bond OH. So this is cinnamic acid. So this reaction also give you the desired product. Okay. So option D also the correct answer. Now next question. The appropriate reagent required for carrying out the following transformation. This kind of reaction. Actually, this kind of reaction takes some much more amount of time. Okay, why? Because we want to analyze each reagent, and each consecutive reagent give you some specific reaction. So I am taking here first option A, that is succinic anhydride. What is that succinic anhydride? This one. The presence of AlCl3. So we know that this is Lewis acid. So what will happen? It will undergo this kind of adduct. So what will happen? It will undergo aromatic electrophilic substitution reaction. Right. As a result, you will end up with I'm skipping some problem, some steps. So you'll end up with this product. Now second reagent, that is zinc amalgam HCl. Zinc amalgam HCl, you know that this is Clemmensen reduction. Clemmensen reduction. So that selectively reduce carbonyl compound that is not carboxylic acid. So this give you methylene functional group. It is not affected on carboxylic acid. Now in the presence of phosphoric acid, again this fellow undergo another step of aromatic electrophilic substitution reaction. Finally you will end up with it becomes H plus, and this kind of attack may takes place, and finally you will end up with this product. Okay, what is that? This is your desired product. Okay. And all other step will not give you, all other, I am skipping all other step, that all other not give you the desired product formation. Maleic anhydride, succinic anhydride, that will not give you maleic anhydride, that is nothing but you will have a double bond here. Double bond will not give you. And phthalic anhydride, that is nothing but this fellow, phthalic anhydride, that will not give you this desired. And maleic anhydride is nothing but this fellow, and this fellow now will not give you this desired product. And here one of the succinic anhydride also given, but that is FeCl3, not AlCl3. And in the presence of lithium aluminum hydrate is a drastic reducing agent that give you only alcohol, not this conversion. So we can omit some by logically other options without doing the whole practice. Here succinic anhydride, we know that this is ideal candidate for this conversion, and maleic anhydride not good candidate, and phthalic anhydride not good candidate. So we can omit all other options. So option A is the correct answer. And the sequence of 3 steps involved the following conversion is. This is also very wonderful reaction. This depend upon the aromatic electrophilic substitution reaction. Aromatic electrophilic substitution reaction. Now we want to produce this compound. I am taking the first option, right? Friedel-Crafts alkylation. Friedel-Crafts alkylation. We want to convert this. We know that in Friedel-Crafts alkylation having some kind of limitation, that is polyalkylation rearrangement. Suppose if you want to prepare normal propyl, that is this generally a simple conversion. If you are trying to produce this compound, that is normal propyl benzene. So if you are dealing with Friedel-Crafts alkylation, we are taking this as a reagent plus AlCl3, and it give you most stable carbocation, this one. This will not give you normal propyl benzene, it give you isopropyl benzene. So first Friedel-Crafts alkylation give you rearranged product. So in this conversion, the first step Friedel-Crafts alkylation will not give you the desired reaction. Moreover, you need to know the directive influence of substituent, and that is further electrophilic substitution reaction orientation. Okay. So I am taking so first Friedel-Crafts alkylation option we can omit. Why? Because it will give you rearranged product. And suppose if you are taking Friedel-Crafts alkylation first, suppose I am taking first option Friedel-Crafts alkylation first, that is a normal propyl, this propyl in the presence of propyl bromide and AlCl3, that first give you this rearranged product. Right? Because most stable carbocation is that. Again, if I am doing Friedel-Crafts other reduction, reduction function, reducing functional group here. So first option we can clearly omit. And another Friedel-Crafts alkylation reduction, no reduction function group here. Reduction means we want any carbonyl function group or other labile function group. Okay, so Friedel-Crafts alkylation, Friedel-Crafts acylation. If you are doing Friedel-Crafts acylation here, what will happen? I am taking some acyl compound, that is some acyl compound like this. So I want to produce this. So some acyl compound like this. Now the directive influence of this alkyl will be ortho para. So para will be the major product. So you will end up with this kind of product. This is not our desired reaction. So our desired reaction give you by the option B. We can check whether it will happen or not. So I am taking option B, Friedel-Crafts acylation. So by evaluating the product acylation, so you should use propanoyl chloride as an acyl compound. Okay, so acylation, the Friedel-Crafts alkylation, reduction. So reduction here, so you should have a carbonyl compound. So I am taking this fellow as an acyl 1, 2, 3. So 1, 2, 3. So this fellow as a acyl compound. So that give you this product. Now second step is Friedel-Crafts alkylation. In this sequence I am taking normal propyl bromide in the presence of AlCl3. Now the directive influence of carbonyl function group is meta. It is meta. That already we have learned. And moreover, this give you rearranged how it is, that give you rearranged product. We are in the presence of AlCl3. Initially it give you this carbocation, but this carbocation undergo 1,2 rearrangement or 1,2 shift. So that give you this carbocation. So that carbocation play the major role here, and will like this. Further reduction means you should use Clemmensen reduction, zinc, amalgam, HCl. So that give you desired product. Okay. So option is option B. Okay. Now this is the next question. Same type of question. Someone asked the question. You want to convert, or you want to carry out this conversion. So you need to choose the correct reagent. So first of all, evaluate what kind of changes have been happened. So this CHO functional group is retained in this reaction, but this ester functional group is converted to alcohol. Okay. So I am taking each reagent for understanding the utility. First of all, if I am taking the option A, that is CHO and CO2ET, first sodium borohydrate, that will reduce aldehyde selectively, not ester. So you will end up with you will end up with this product. It will not affect on ester functional group. Then next reagent is hydrolysis H3O plus that give you this product COO. No, that is our product. So option A will not give you the desired conversion. Now what about option B? Option B, that is lithium aluminum hydride LiAlH4. That will reduce both the aldehyde and ester corresponding alcohol. This is not our desired conversion, no. So option B not give you the desired reaction. So the basic thing is that you want to convert one of the functional groups selectively, or you want to carry out a reaction selectively. That is called chemoselectivity. So you want to carry out reaction on least reactive ester only, not aldehyde. So in this scenario, we should choose a strategy called protection deprotection. So that is the correct answer. Here we are choosing C. So I can illustrate. I am taking our compound, that is our compound is this one. Here we have aldehyde functional group. Here we have ester functional group. So here aldehyde is more reactive functional group towards nucleophilic addition, least reactive. So you want to carry out a reaction at this site, not this site. For that we are choosing protection strategy. That means you are masking one of the functional group where you are not supposed to carry out any reaction. So in this problem, you are going to mask this aldehyde. Now selectively you are doing your desired reaction on this least reactive ester. So for that, first of all, as you given with the option C, you are taking 1,2-diol. That is this fellow. This fellow in the presence of H plus, that will protect your highly reactive aldehyde like this. This is called acetal. Okay, not like this. It will protect like this. It will not affect on this ester. So now your aldehyde is protected. Aldehyde is protected by means of acetal. Okay, by means of acetal. Now you can do the desired reaction on this ester by using second reagent, that is lithium aluminum hydride. So lithium aluminum hydride, that will reduce your least reactive ester functional group to like this. So it will give you alcohol. Now next reagent is H3O plus. That is the step is called deprotection. That give you back the protected functional group, that is aldehyde as such. Now this is your desired product. So option C is the correct answer. Now another option also is there. That option is correct for first step. That is, it is also used for the protection of aldehyde functional group. That is, if you are using thiol, 1,2-thiol instead of alcohol, that also used for the protection of aldehyde functional group. But for D protection, you have to choose Mg2 plus salt, any Mg2 plus HgO or HgCl2 like this. Then only give you the carbonyl functional group back. But you are given with the H3O plus for D protection, so it won't be used for the desired conversion. Ready? Now this is the another question. The major product YZ in the following reaction sequence are. So this reaction, you want to carry out this reaction, then only you will end up with the desired product. So we can start with the first, that is PHNH2, that is aniline. And next reagent, you know, it is a alpha beta unsaturated ester. So clearly you know that this is a nucleophile. So it can undergo 1,4 addition reaction like this. So you will end up with a NH2 plus, it becomes NH O minus OET. It is NH2 plus, after deprotonation it becomes NH, and the tautomerism will take place. Here tautomerism will take place. That give you PH NH O E T. But you are using this alpha beta unsaturated compound in excess. That means this fellow again undergo one more 1,4 addition reaction like this. Right. Here you have one more 1,4 addition reaction will take place. Right. So again you will end up with a product like this. PH here, first, second, OET, OET. Now that is a product to Y, right? This is Y. Now what will happen next step? What will happen in the next step? ETONA H3O plus. So I am taking this compound, the next page, that is I think one more carbon is there, right? One more carbon is there. 1, 2, 3. 3 carbon should be there. 1, 1, 2, 3. OET. I'm taking here second step. OET. 1, 2, 3. OET. Okay. Now, sodium ethoxide, that is the reagent. You know, this is a well-known name reaction. That is, OET minus comes to the picture. It will abstract one of the acidic hydrogen from here, and it will form carbanion or enolate ion. Okay, so that enolate comes to the picture or carbanion comes to the picture. It will attack on this another equivalent of ester. So this is a diester, and this is a intramolecular Claisen condensation reaction. Is intramolecular Claisen condensation reaction. Okay. Now you will get a ring formation. That is, you want to give the number 1, 2, 3, 4, 5, 6. So you will end up with the 6-membered ring. Then give the same number here. So 1, 2, 3, 4, 5, 6. So first position, you will have this ester, and the sixth position, what will happen? A carbonyl function. Okay. Again, that is the first reagent. So this condensation reaction will happen. Now again, NaOH H3O plus heat. That means ester hydrolysis or saponification is called saponification. That means you will end up with the corresponding sodium salt of carboxylic acid. Sodium salt of carboxylic acid or carboxylic acid. Now heat means you will end up with the decarboxylation. You will end up with the decarboxylation. So your product is this is the product. So option, the correct option is, option B is the correct answer. Option B is the correct answer. Clear? So these kind of reaction you have to learn name reactions, but if you have some logic idea, you can succeed. If you suppose in this situation you are not aware about this name reaction, you can do this reaction by your logic. No confusion, no complication here. Okay, this is some intramolecular Claisen condensation having some other name. Okay, great. Now this is another question on reaction with the sodium nitrate and HCl. which of the following amino alcohol give you the compound P? You need to produce this compound P. So basically, this is diazotization, and this reaction is called semi-phenolic rearrangement. Generally, semi-phenolic rearrangement. So in cyclohexane, in chair conformation, the condition is that, suppose I'm taking simply one situation. So simply I'm taking this OH here and NH2 here. Suppose I'm taking like this, and we know that both are axial, right? And they are called anti-periplanar. That means this functional group and this functional group, they are anti-periplanar. That means dihedral angle is 190 degree. That is, these are departing or group, those are participating in reaction. So after diazotization, NaNO2 HCl, you will end up with the diazonium salt, right? That is N2 plus here and OH here, right? OH here. Now, in semi-phenolic rearrangement, we know that migrating group, sorry, I am taking here OH here and H here. So I am considering these are anti-periplanar, not OH. H and NH2, they are anti-periplanar, right? So now H here and OH. Now we know that in phenol rearrangement, what will happen? 1-2 shift takes place. Now next step, 1-2 shift takes place. So the condition is that the migrating group should be anti-periplanar with this N2 plus. The condition is that migrating group should be anti-periplanar with this N2 plus. That means this H is anti-periplanar with this N2, that it will migrate. So reaction happen like this. This group comes and this will migrate this portion and this get eliminated. So your product will be like this. Like this. So condition is that migrating group should be anti-periplanar with the leaving group. But you need to produce this product, not this product. So this which one give you the desired product. So we can analyze each and every reactant for your knowledge. So first compound I am taking here. This is tertiary butyl group. It is a locking group. That means this compound will not undergo flipping. This is a rigid compound. So N2 here, this N2 becomes N2 plus after diazotization and OH here. That means you are departing, your hydrogen is anti-periplanar with this N2 plus. After semi-phenolic rearrangement, what will happen? This group get migrated from here to this position. This get eliminated, and you will have a carbocation here. That carbocation is nullified by this shift. So you will end up with this product. Now what about the second I am doing here. After diazotization, you will end up with the N2 plus here, OH here. Now, which group is anti-periplanar with this N2? That is the question. Is there any hydrogen? The first thing is that if your substituent is equatorial, no anti-periplanar relation. In order to have anti-periplanar relation, your N2 plus should be either axial upward or axial downward. These situations only give you the axial relationship. Otherwise, it will be equatorial relationship. Axial relationship means this N2 plus having anti-periplanar hydrogen here, another anti-periplanar hydrogen here, and here also anti-periplanar hydrogen here, anti-periplanar hydrogen here. Okay. If it is in axial upward or axial downward. If it is equatorial, then the CC connection, that is CC connection, this CC connection is anti-periplanar with this. So what will happen? Instead of hydrogen, that CC bond will migrate. And ring size get reduced. So how it is? It becomes like this. That is, it will be 5-membered ring, and here it is aldehyde. So that is nothing but, and it is pointed out downward, that is nothing but, it is upward, right? That is nothing but planar structure is downward. CHO 1, 2, 3, 4. 1, 2, 3, 4. Fourth position, it is upward. So in wedge, it is this fellow. Okay. So clearly, B give you the desired product. Now you can simply check C and B. So now you can derive a shortcut. In ring reduction, your NO2 should be equatorial. And if there is any ring reduction, your NO2 should be axial upward or axial downward. Okay. Now here it is equatorial, here it is axial, right? So clearly this will not give you any ring reduction. This give you another reaction. So we can check what reaction it is. So here what will happen? I'm doing the reaction here itself. So after diazotization, it is N2 plus, and here it is OH. And which bond is anti-periplanar with this N2? This bond is anti-periplanar with this, and it will undergo 1,2 shift in semi-pinnacle rearrangement, and you will end up with the desired product. So option C also give you the desired reaction. So since it is MS2, you have to select B and C. What about in the case of D? What about in the case of D? So after diazotization, you will have N2 plus in axial portion, but axial upward. But in axial downward, you have OH, not H, not H. So they will undergo not a semi-pinnacle rearrangement. In semi-pinnacle, we have seen 1-2 shift, right? 1-2 shift of antiperiplanar group. Now you cannot have 1-2 shift of OH function group. So instead of 1-2 shift, they will undergo this epoxide formation. This lone pair will attack and this get eliminated. Now you will have this kind of epoxide. Let's point out downward. So this is the another unusual reaction with this. All other give you semi-pinnacle rearrangement. In the case of ring reduction, your NH2 group should be equatorial upward or downward. That give you reduced ring reduction. And if there is any ring reduction, then your N2 plus or NH2 should be either axial upward or downward, provided it should have antiperiplanar hydrate. Okay, clear. So option C and B are the correct answer. Now this is the next question. So this is another name reaction. So as you know, this TiCl3 Cu zinc, that is a name reaction is called McMurray coupling. What is the utility of McMurray coupling? It get coupled, that is in the presence of TiCl3, two equivalent of a carbonyl function group get coupled and it produce alkene in the presence of TiCl3 and linear aluminum hydride or copper zinc. Okay. So clearly this compound, two equivalent of this compound get coupled, OMe, this is carbonyl function group of first compound, and another carbonyl compound comes to the picture. So they get coupled and it will produce a common alkene like this. Now 1, 2, 3, OMe, PH, okay, OMe, PH, and double bond. So this is the coupled product after first reaction. Now second reagent is HCl H2O. That means you will undergo some tautomerism here. So suppose if you have a functional group, simply if you have an enolate, this enolate, what will happen? This enolate undergo keto-enol tautomerism, right? So it will produce keto function. Similarly, if you have this kind of OMe, methoxide, and this kind of enolate, in the presence of acid, these also give you carbonyl function. So similarly, these two and give you corresponding carbonyl functional group, so that give you the dissociated product. So which option is the correct one? Option C is the correct one. So this is the multiple step question, and you need to use one main reaction, that is McNebeck coupling. Now this is the next question. The major product XY in the following reaction sequence are. So simply this is a MEMGBr right, in the presence of ether. This is Gilman's reagent, and this is alpha beta unsaturated carbonyl compound. As you know, it will undergo 1,4 addition, right? So Me minus comes to the picture. It will undergo 1,4 addition. O minus, and this is Me, right? This is Me. Okay. Now, next reagent, you should aware about the next reagent, that is methyl iodide. It will undergo some alkylation reaction. If you have any enolate, it can undergo alkylation. Enolate means it is just like carbanion. Simply, this is a carbonyl compound. If you have a carbanion like this, it can undergo some delocalization like this, right? So it will produce this enolate. This is nothing but carbanion, but we are expressing reaction by means of enolate. So carbanion, enolate, the utility is the same. This is the nucleophile. Okay. So after this, it will produce this compound Me here and 2Me here. Okay. Now next MCPBA, that is MCPBA. It is a well-known reaction, that is Bay-Williger oxidation or rearrangement. Here, two side here. Okay, so here I am two side here. One is this blue side, another one is this red side. So in Bay-Williger oxidation, your oxygen insertion will take place at electron rich site. So clearly this blue site is electron rich. So oxygen insertion in Bay-Williger oxidation will take place at this blue site. And your product will be like this, and 6-membered becomes a 7-membered ring, and your correct option is option D, right? Option D is the correct answer. So without any delay, you can simply give the answer by looking the option A, B, right? So by evaluating this step, you understood it is a 1,4 addition. So 1,4 addition, right? Like this. So here no 1,4 addition, it is 1,2 addition. So as you studied earlier, if you have Grignard reagent only, it will undergo 1,2 addition only. 1,2 addition only. This 1,2 addition is also 1,2 addition, but here 1,4, here 1,4. So simply you can omit these two options. Why? Because it is the resultant of 1,2 addition. But C and D are 1,4 addition. So next, those are determined by means of their oxygen insertion procedure. So here oxygen inserted electron deficient site. So here oxygen is inserted on electron rich site. So clearly without performing this step, you can give the answer D is the correct. Okay. Now this is the 10th question. This is somewhat deviated, some high level question. Okay. So only one reagent is the metachloroperbenzoic acid, that is MCPBA is only the one of the reagent. So we can do this reaction. So I am taking this reagent. This is our reactant. I'm doing here. So MCPV, what is the utility of MCPV? Two utilities there. One is what we have mentioned earlier. One is Weyerhaeuser oxidation. If you have an alkene, it will form epoxide. It will form epoxide. Okay. So clearly here you have an alkene, so it will form an epoxide here. It will form an epoxide here, no doubt at all. Okay. Right. Now this option, this kind of option, no option like this, right? But some other reaction might be happen here, right? So it will undergo some kind of a rearrangement. So Wagner-Mervin rearrangement in order to produce a most stable carbocation. So MCPB, it is an acid. It can undergo some protonation. So here you can have protonation, either this epoxide or alcohol. So since this epoxide is the 3-membered ring, it has some ring breaking tendency or affinity towards proton, right? Like this. So it will undergo protonation readily. Like this. So now the driving force for ring rupture. Okay, this is the driving force for ring rupture. That is, here you have a positive charge. That's why you need to cleave one of the CC connections. So clearly, I am taking this bond and another. So suppose this bond is being broken. So what will happen? Watch here, and this becomes like this, and here you have a positive charge. Now that is the Wagner-Mervin rearrangement play here. What is the driving force? Here you have a cation. This is nothing but tertiary carbocation. But if you perform 1,2 shift here, you can have a more stable carbocation, that is a mesomerically stabilized carbocation. Here you have an OH group. If you produce a carbocation in this side, you can have much more stable carbocation. That's why it will undergo 1,2 shift like this. 1,2 shift like this. Okay, 1,2 shift. So your answer, your product will be like this. Okay. Now what will happen? This lone pair electron will shift and it becomes keto function group. It becomes keto function group. So I am writing here itself. Keto function. Now I am redrawing this compound. How it is. You need to end up with the no product like this. So I am redrawing this. So I am giving the number. You just see the numbering 1, 2, 3, 4, 5, 6. So I can get an orbornate 6 system. So 1, 2, 3, 4, 5, 6. So mark the function group 2. Second position having a carbonyl function group, and third position having 2 CH3, right? And any other bridge link between 1 and 4. Is there any option like this? Moreover, you have, okay, I forgot that here you have an OH function. I forgot. Here you have a OH function with CH2OH. That also reflect in 1. That's also reflected in 1. So option B is just like that. Okay. So the correct answer is option B. Okay. Now we have discussed 10 questions. Okay. Now, thank you.